Welcome to the video on Digital CMOS VLSI Circuits, Course 20 EC214, offered by the Department of Electronics and Communication Engineering. I am Mr. R. Chandru, Assistant Professor. We are focusing on Module 1, MOS Transistor and Processing Technology. The VLSI Design Flow begins with system specification, where functionality, performance, power, and area constraints are defined. This is followed by architectural design, where system-level decisions, such as data path and control, are established. The design is described at RTL using HDLs and verified through functional simulation. Next, logic synthesis converts RTL into a gate-level netlist, followed by logic verification. Circuit design refines transistor-level implementation, and timing, power, and noise are analyzed. Physical design includes floor planning, placement, and routing, followed by layout verification, such as DRC and LVS. Finally, the design proceeds to fabrication, packaging, and post-silicon testing. System specification is the first and most critical step in the VLSI design process, where the complete requirements of the system are defined in detail. It provides a high-level abstraction of the system, describing what the chip must do without specifying how it is implemented. At this stage, key factors such as performance, functionality, physical dimensions, design methodology, and fabrication technology are carefully considered. Performance includes speed and timing constraints, while physical dimensions relate to chip area and packaging limitations. Design methodology and fabrication technology determine feasibility and scalability. Additionally, power consumption, cost, and reliability are also important considerations. Ultimately, system specification involves making trade-offs between performance, power, and area, commonly referred to as the PPA trade-off, while balancing market requirements, technological feasibility, and economic viability. Functional design, also known as architectural design, focuses on identifying the major functional units of the system and defining their interconnections. At this stage, the system is described at a behavioral level, specifying what operations need to be performed without detailing the hardware implementation. Key parameters, such as area, power, and performance of each unit, are estimated. The design captures input, output, and timing requirements of each block. For example, a multiplication operation may be specified without deciding the exact hardware architecture. The emphasis is on behavior rather than structure, ensuring a clear and efficient system-level organization. Logic design translates the system architecture into a precise digital representation using Boolean expressions and control flow. At this stage, important decisions such as word length, data paths, and register allocation are defined. The outcome is described at the register transfer level, or RTL, which specifies the movement of data between registers under clock control. RTL is implemented using hardware description languages, such as Verilog or VHDL. This description is used for functional simulation and verification. Since the design is expressed in Boolean form, logic minimization techniques can be applied to optimize area, power, and performance. Circuit design translates the logic-level representation into an actual transistor-level implementation. The Boolean expressions obtained from logic design are mapped into circuits using logic gates and MOS transistors, considering speed, power, and area constraints. At this stage, detailed design of gates, transistor sizing, and interconnections is performed. The result is a circuit netlist that describes the electrical connectivity of the system. Circuit simulation, typically using SPICE tools, is then carried out to verify functionality, timing, and power consumption under different operating conditions. Physical design converts the circuit-level netlist into a geometric representation known as layout. In this stage, each component, such as transistors and interconnections, is represented as geometric patterns on silicon. The process includes floor planning, placement, and routing of components. All connections are realized using metal layers based on design rules provided by the fabrication technology. The layout must strictly satisfy design rule constraints to ensure manufacturability. Various verification steps, such as design rule check and layout versus schematic, are performed to ensure correctness. This stage is highly complex and directly impacts chip performance, area, and yield. Fabrication is the final stage of the VLSI design flow, where the verified layout is physically realized on a silicon wafer. The process involves multiple steps, such as photolithography, deposition, oxidation, diffusion, and chemical mechanical polishing. Each layer of the circuit is created using masks, making the process highly precise and technology-dependent. After fabrication, the wafer is diced into individual chips, packaged and subjected to rigorous testing. Before mass production, prototype chips are evaluated to ensure functionality, performance, and reliability. This stage ultimately transforms the design into a real, working integrated circuit. After fabrication, individual chips are packaged to provide mechanical protection and electrical connections. Packaging involves mounting the chip onto a package and connecting it to external pins using wire bonding or flip chip techniques. The packaged chip is then placed on a printed circuit board or integrated into multi-chip modules. Each chip undergoes rigorous testing to verify functionality, timing, and reliability under different operating conditions. Any defects are identified and analyzed during debugging. This stage ensures that only fully functional and reliable chips are delivered for practical applications.
Thank you for watching this video on the VLSI Design Flow within the Digital CMOS VLSI Circuits course.